Have you ever thought about this? Human probes have already flown all over the solar system. There are rovers currently moving on Mars. Humanity has dropped probes into the clouds of Saturn and has taken photographs of Pluto from less than 13,000 kilometers away. Crossing billions of kilometers of space seems to have become completely commonplace today. But there is one direction humanity has almost never truly traveled. Logically speaking, it should be the absolute easiest place to reach. Yet it has ironically become one of the hardest destinations. That is escaping the solar system vertically. Not flying toward Mars, nor flying toward Jupiter, but flying straight up or straight down relative to the solar system plane. Sounds incredibly simple, right? Just point the rocket upward and fly. But the real problem is that physics simply does not allow you to do this easily. Coming up next, you will see exactly why escaping the solar system vertically is even more difficult than flying to Pluto. You will also find out what a probe would actually see looking down upon the solar system if it ever completes this journey in the future. Scientists are even considering an extremely bizarre maneuver right now, letting a probe intentionally dive toward the sun first, and then using the sun gravitational pull to slingshot itself completely out of the solar system. To truly understand why vertical escape is so incredibly difficult, you first need to realize that you already possess a terrifying amount of speed. At this very moment, Earth is orbiting the sun at approximately 30 kilometers per second. That equates to over 100,000 kilometers per hour. This is not an exaggeration. The entire planet beneath your feet is hurtling sideways at 30 kilometers per second every single second. Naturally, all rockets launched from Earth automatically inherit this immense speed. Whether launched by NASA or SpaceX, their space probes never start from a standstill. The moment they leave Earth, they already carry a lateral velocity of 30 kilometers per second. Usually, this is a fantastic advantage. For example, when flying to Mars, this free speed acts as a massive boost. We only need to adjust our direction slightly and add a few extra kilometers per second to reach another planet. But the problem arises when you want to fly straight up. Not flying toward Mars or Jupiter, but breaking away from the entire solar system plane entirely. At this point, the lateral speed that originally helped us becomes our greatest enemy. Because if you want to travel perfectly vertical, you must first completely cancel out that lateral movement of 30 kilometers per second. After doing that, you still need to generate brand new speed to continue climbing upward. The energy required to do all of this is absolutely astronomical. Scientists use a vital concept called delta V to calculate this difficulty. This metric represents how much additional velocity change a spacecraft needs to generate. Flying from Earth orbit to Mars requires a delta V of only about 4 kilometers per second. However, if you want to fly straight out of the ecliptic plane vertically, you need to cancel out a full 30 kilometers per second. That is almost 10 times the energy required to reach Mars. This creates what we call the orbital prison of the solar system. As Earth orbits the sun, it gives us free directional speed, but simultaneously it locks us tightly within the solar system plane. It is very easy for us to fly along the plane to visit other planets, but it is extremely difficult to truly leave this flat zone. Leaving means you must single-handedly fight against the orbital momentum accumulated over 4.6 billion years. This leads to one of the most counterintuitive facts in astrodynamics. Flying to Pluto billions of kilometers away actually consumes less energy than flying to a position just a few million kilometers directly above the Sun North Pole. Because escaping the solar system vertically is so exceptionally difficult, almost no probe has ever successfully accomplished it. Consequently, even today, humanity knows very little about what exists directly above and directly below the Sun. We currently possess high-definition maps of Mars. We can capture close-up photographs of Pluto, asteroids, comets, Saturn rings, and Jupiter moons. Yet the solar poles, the absolute most critical locations on the star closest to Earth, have almost never been clearly observed by humans. This lack of data is much more problematic than most people realize. The most violent and dangerous solar activities frequently occur in the polar regions. The absolute fastest solar winds originate right there. The massive reversal of the sun magnetic field that happens every 11 years actually begins at the solar poles. Furthermore, the space weather environment of our entire solar system is deeply influenced by the regions above and below the sun equator. The main issue is that humanity has almost exclusively observed the sun from a side angle throughout history. This is exactly like trying to study the complex weather patterns of an entire planet, while being forever restricted to standing solely on its equator. In the entire history of human spaceflight, there have only been 2 missions that truly observed the sun from a top-down perspective. The first occurred in 1990 with the Ulysses probe, a joint mission launched by NASA and the European Space Agency to fly out of the ecliptic plane. This probe had to take an incredibly extreme route. It first flew all the way out to Jupiter. Then it utilized Jupiter's immense gravitational field like a giant slingshot to forcefully warp its orbit completely out of the solar system plane. Finally, it looped back toward the sun at an incredibly steep inclination of nearly 80 degrees. The mission was a resounding success. Ulysses became the very first instrument to directly measure the high-speed solar wind erupting from coronal holes at the solar poles. However, the catch was that this probe relied on equipment built in the 1980s. It simply lacked any capability to actually photograph the solar poles. Therefore, even though humanity detected data from that region for the first time, we still did not visually see it. The second mission is actively underway right now, featuring the solar orbiter launched by the European Space Agency in 2020. Over the past few years, it has been utilizing the gravity of Venus to slowly and methodically raise its orbit. In March 2022, Solar Orbiter finally beamed back the very first authentic photograph of the sun's south pole in human history. The solar poles captured in these images look entirely different from the sun humanity is accustomed to seeing. The polar regions are filled with chaotic and deeply twisted magnetic field structures, bearing zero resemblance to the calm, glowing sphere we see from Earth. When you carefully think about it, until very recently, neither human beings nor advanced robotics had ever truly seen what the top and bottom of the sun actually look like. For this closest, brightest, and most vital star to Earth, humanity has only just begun to photograph its polar extremes. There is a second critical reason why escaping the solar system vertically is so important. To this very day, we actually have absolutely no idea what the entire solar system looks like from the outside. Surrounding the sun exists a massive structure known as the heliosphere. It acts much like a colossal bubble completely enveloping the solar system. The solar wind constantly expands outward, actively resisting incoming materials from deep interstellar space. The interior of this protective bubble is the designated active zone for all planets, comets, and every single human space probe ever launched. Beyond this boundary lies the true deep space of the Milky Way galaxy, a region heavily saturated with lethal cosmic rays and interstellar particles. The heliosphere has actually been actively shielding us from these galactic dangers for billions of years. For decades, scientists firmly believed the heliosphere was shaped somewhat like a comet. Theoretical models depicted it as bulbous at the front, dragging a remarkably long tail behind it. Since the solar system physically moves through the galaxy, it constantly collides with the interstellar medium. Therefore, the long-tail comet-shaped heliosphere became the standard model printed in textbooks everywhere. However, in 2020, a dedicated research team from Boston University proposed a completely contradictory conclusion. After constructing advanced models using brand new NASA data, they discovered that the heliosphere might not be comet-shaped at all. Their newly developed model resembles a flattened croissant. It bulges significantly in the middle, features short jets erupting from both sides, and entirely lacks that famous long tail. The lingering problem is that we still cannot truly confirm either theory to this day. This is because humanity has never actually observed the heliosphere from the outside, nor have we ever sent a probe high enough above the solar system to observe the entire structure from a true top-down vantage point. Although the famous Voyager probes have successfully flown outside the heliosphere, they still essentially exited sideways along the flat solar system plane. Their data is incredibly useful, but far from sufficient. If humanity genuinely wants to know exactly what our solar system looks like while navigating the galaxy, there must be a dedicated probe that actually flies high above the solar system and then looks straight back down at the entire structure. NASA is currently developing a mission named IMAP, which stands for the Interstellar Mapping and Acceleration Probe. Its primary objective is to intricately remap the complex structure of the heliosphere from within the solar system. The glaring problem remains that up until now, absolutely no probe has ever reached that high vertical angle. We literally live inside the heliosphere, yet we do not even know its true physical shape. So how exactly can humanity solve this massive problem of vertical solar system escape? The definitive answer might be completely different from what you would intuitively think. You absolutely cannot solve this simply by building larger and more powerful rockets. The sheer amount of energy required to mechanically cancel out Earth's massive intrinsic orbital velocity is completely absurd. Achieving this is nearly impossible using any standard payload of chemical rocket fuel. Consequently, scientists began heavily considering an extremely counterintuitive method. This radical concept has even started transitioning from pure theoretical physics into genuine mission architecture. It is officially known as the solar Oberth maneuver. The foundational logic of this maneuver is almost the exact opposite of what the general public would imagine. A normal person would logically assume that a spacecraft trying to escape the solar system should aggressively push outward. But this specific plan does the exact reverse. It dictates that the spacecraft must first intentionally plummet directly toward the sun. The spacecraft will continuously free fall toward the sun, accelerating to wild extremes under the immense solar gravitational pull. When it reaches its absolute closest approach to the sun, its physical speed could easily exceed 100 kilometers per second. Then, at the most dangerous split second imaginable, it completely ignites its thrusters. The foundational reasoning for this comes from a brilliant principle proposed by German physicist Hermann Oberth in 1929. Igniting a rocket engine while traveling at highly extreme speeds yields a vastly greater boost in orbital energy compared to igniting at low speeds. The exact same unit of fuel utilized near the sun will generate an effect far exceeding its use in ordinary empty space, specifically because that location is the deepest gravity well in the entire solar system. Therefore, the closer the spacecraft gets to the sun, the more incredibly efficient a single acceleration burn becomes. The chemical fuel originally brought all the way from Earth will be explosively converted into a massive amount of kinetic energy near the sun. Immediately after completing the burn, the spacecraft will attain an extreme velocity and finally break completely free from the flat solar system plane, blasting violently outward toward the solar poles. In other words, the terrifying process of diving into the sun itself, paradoxically, becomes the ultimate takeoff runway. In addition to this, scientists are also actively evaluating another elegant solution utilizing solar sails. Several advanced mission concepts, such as the Proteus Solar Polar Imaging Plan and high-inclination solar missions, intend to deploy massive solar sails to gradually alter their flight paths. These probes do not require traditional chemical thrusters. Instead, they harness the physical radiation pressure of sunlight itself to propel the spacecraft. Colossal metallic membranes will act exactly like wind sails, being slowly but relentlessly pushed by solar photons. Although this delicate process might easily take several years, it consumes virtually zero internal fuel. Furthermore, the longer the sail operates, the higher the orbital inclination can be mathematically pushed. Because of these distinct advantages, scientists are now actively exploring combining both methodologies. They plan to first use a solar sail to slowly maneuver closer to the sun. Then they will flawlessly execute the high-speed Oberth maneuver right at perihelion. Finally, they will continue deploying the solar sail to effortlessly carry the probe all the way up above the solar system. Many astrodynamics researchers firmly believe this might be humanity's first genuine opportunity to clearly see the extreme solar poles. If a future probe truly manages to fly directly above the solar system, what exactly will it see? First and foremost, the entire visual perspective will fundamentally change. The solar system plane is actually an incredibly dirty environment. Earth and all the other terrestrial planets are constantly plowing through a massive ambient dust cloud. This pervasive dust originates from billions of years of disintegrating comets, violent asteroid collisions, and the continuous long-term mechanical wear and tear of the entire solar system. You can actually see this ancient debris with your own naked eyes. On exceptionally dark, clear nights, shortly after sunset or right before sunrise, a faint, pyramid-shaped glow will sometimes majestically appear in the sky. That specific phenomenon is scientifically called zodiacal light. It is actually just pure sunlight physically reflecting off the ambient dust scattered across the solar system. Essentially, you are visually observing the entire solar system plane itself, glowing in the dark. If a highly advanced probe truly flies vertically above the ecliptic plane, after several months of travel, it will slowly rise completely out of this dense dust layer. The optical field of view up there will be infinitely cleaner. There will be drastically less scattered light and almost zero background fogging. For highly sensitive astronomical telescopes, this represents one of the most structurally ideal locations imaginable. Many incredibly faint cosmic signals that would normally be obscured by ambient dust within the inner solar system can be seen with pristine clarity up there. Prime examples include searching for faint biological biosignatures around distant exoplanets, flawlessly measuring the cosmic microwave background radiation, or even structurally re-examining the Milky Way galaxy from an external vantage point. Beyond all of this, the local environment surrounding the sun itself would feel completely alien. Near the solar equator, the solar wind speed maxes out at only about 400 kilometers per second, and its physical flow is incredibly chaotic. But once you reach the extreme solar poles, the physical situation changes completely. High-speed solar winds erupting at velocities reaching 700 to 800 kilometers per second dominate the region. They aggressively blow outward like a remarkably steady and continuous torrent of high-energy particles. If a future probe truly achieves flight high above the ecliptic plane, the solar system it photographs will look completely unprecedented. From that extreme vertical angle, the entire solar system will visually appear as a gigantic cosmic disk. All the planets will align into a flat ring-like structure, perpetually orbiting the central star. Meanwhile, the ancient zodiacal dust will beautifully drift over the entire plane like a thin, glowing mist. Further out into the deep void, the entire system will be safely enveloped by the massive heliosphere, whose true geometric shape remains a profound mystery. Humanity will finally look down upon our cosmic home for the very first time, capturing the exact same profound feeling as when humanity first looked down at Earth from outer space. But up until today, absolutely no human being nor any autonomous robot has ever actually captured this breathtaking image. We are still deeply trapped within the inner boundaries of our solar system, forever gazing upward at our own cosmic home. You know, the story of escaping the solar system vertically is not just a complex physics problem. It is actually a beautiful metaphor for our own lives. We are so often trapped in our own personal orbital planes, the daily routines, the comfort zones, and the invisible momentum that keeps us moving in the exact same horizontal direction every single day. It is easy to just go with the flow. But to truly make a breakthrough, to fly vertically, and see the big picture of your life, you sometimes have to completely break your existing momentum. In fact, just like the solar Oberth maneuver scientists are planning, sometimes we have to bravely dive straight into the sun of our own lives, our biggest challenges, our deepest fears, and our greatest risks. Because it is exactly by facing the intense heat of our struggles that we can slingshot ourselves forward and gain the massive momentum needed to reach unprecedented heights. Sometimes, falling into the fire is the ultimate takeoff runway. But hey guys, all the scientific scenarios, concepts, and analyses we just went through are based on my personal synthesis and perspective. They could be completely right, or they could be totally wrong. It could be our grand future, or just a crazy illusion. So, what do you guys think about all of this? Do you think these theories are real or just science fiction? Will humanity actually break out of this orbital prison? I genuinely want to hear your thoughts. So leave your opinions down below so we can debate and discuss it together. And before you go, I am incredibly curious about one thing. Right at this exact moment, what city or country in the world are you watching this video from? Because no matter how far apart we are on this tiny pale blue dot, we are all looking up at the exact same sky. Drop your location in the comments and let me know. I will see you all down in the comments section. Thank you so much for exploring the universe with TIAN Science. Have an absolutely amazing day.